In this video, I'm going to talk a little bit about error propagation and taking weighted averages. Some supporting documents about this may be found in the supplemental materials at the end of the lab manual. Okay, so let's suppose that we've got some quantities and we've measured them and they have some uncertainties. So for example, maybe we have a quantity u that has some uncertainty that we're going to call sigma u, and some other quantity v that has an uncertainty sigma v. So these could be, for example, a distance and a time. Maybe we've measured how far something has gone, and we measured how long it took to go that far, and we've got uncertainty estimates for both of those. And now we want to say, what's the average speed that the thing had when it went that distance during that time? And the question is, we can calculate the speed easily enough, but how do we take our uncertainties for the position or the distance and the time and turn that into an uncertainty for the speed? So you've learned how to do this probably in university physics. You probably learned some formulas for if there's a product or a sum or a quotient or things like that. And what we're going to do is write down what the general expression is, because in this course sometimes you'll come up on some things that are a little bit more complicated. So it turns out that if you have a number of quantities, say u and v, and we could just keep going down, maybe to some other quantity that we'll call z, and they all have uncertainties, and now we want to calculate some function that is a function of all of these things. Let me try that again. So it's a function of u and v and all the way out to z. And we want to figure out what is the uncertainty in this, if all of these quantities u, v, etc. down to z have uncertainties themselves. So it turns out that the answer, and I have a reference to a book in the lab manual that you can look at if you like. It turns out that the answer is that what we need to do is calculate the partial derivatives of the function with respect to each of these quantities and sum up the squares of those multiplied by the uncertainties. So we're going to calculate partial of u, or f, with respect to u, square it, multiply by sigma u squared. Do the same thing for v, square it, times sigma v squared, etc. And just keep doing this for all the variables. Now there's some subtleties here. We're going to evaluate these partial derivatives at the locations that are at the values of u and v, etc., that we measured in our experiment. Also, I should mention, maybe not all of you have seen partial derivatives before. All a partial derivative means is take the derivative with respect to one variable while holding all of the others constant. Okay, so let's do an example. Suppose that we've got a sphere. We know its radius with some uncertainty. We know its mass with some uncertainty. And we want to calculate what the density of that sphere is. So, all right, so our function then is a function of the mass and the radius. F is equal to the mass divided by the volume, which is 4/3 pi r cubed. Now, for taking partial derivatives, I find it easiest to write this as 1 over 4 pi over 3 times m r to the minus 3 power. Okay, so now we can go ahead and take the derivatives. The partial of f with respect to r is equal to, so we're just going to take the derivative here with respect to r, leaving m fixed. That's what it means to do a partial derivative. So we're going to pull down the exponent of 3 there. We get minus 9r to the minus 4 m divided by 4 pi. Can do the same thing with respect to m. It's nice and linear in m, so that's easy. So it's 3 over 4 pi times r to the minus 3rd power. Great. Okay. So now let's calculate what sigma f is. So sigma f, the uncertainty in this quantity. So f here, so u and v, by the way, are like r and m, or m and r, doesn't matter. And f is this function of these two variables. It's the density. Okay, so we're finding the uncertainty in the density. So what we're going to do is put our two expressions in here and square them. So we've got minus 9 mr to the minus 4 over 4 pi, quantity squared. And now we're going to multiply by the associated uncertainty squared, so sigma r squared. And then do the same thing for partial of f with respect to m, so that's 3 over 4 pi squared r to the minus 6 and sigma m squared. All right, now that's a pretty nasty looking expression. If you put that into Excel or something, pretty easy to make a mistake, right? You got 3's and pi's and stuff floating all over the place. It turns out that if you have a product or a quotient or products and quotients of powers, it's basically always easiest to do this, to find the relative uncertainty. So we'll take the uncertainty and divide by the original function. And if you do this, I'll spare you the details, but you can check this on your own. If you do this, what you're going to find is that things cancel out really nicely. And what we end up with is 9 sigma r over r squared plus sigma m over m squared. And you can see that that's a much nicer expression to work with. So what you would need to do here then is you take your uncertainty in r and divide it by r and square it, multiply by 9, and then uncertainty in m divided by m, square it, add these two guys together, then take the square root, and then when you're done, because you're trying to find sigma f, you got to remember to take f back over on the right hand side here and multiply by f, right? So sigma f is equal to f times the square root of all that stuff. You got to take the f and put it over on the other side. What you're calculating directly is the relative uncertainty, but what you might want is the uncertainty itself. Okay, so then you have to multiply by f when you're all done. That's an easy thing to forget to do. Okay, let's pause here for a second and take a look at that factor of 9, because this is kind of interesting. So we've got this factor of 9 that is right here. If you look back through the calculation, you'll see that where that 9 came from is right here. When we took the derivative, we had this minus 3 that came down, and the minus 3 eventually got squared, so the 9 here is really minus 3 squared. For the m was to the power 1, and here we have really a 1 squared. Okay, so these powers in our original expression, m to the 1, r to the minus 3, ended up getting squared here in front of these relative uncertainties squared. What that means is that if your relative uncertainty in r, sigma r over r, say like you can think of that as being is a ratio, it's sort of a fractional uncertainty, if that, sigma r over r, is the same size as sigma m over m, the effect due to sigma r over r is much bigger because we have this 9 here, because that comes back to the fact that it was 1 over r cubed, and so that minus 3 power gets squared, and it leads to a bigger effect in our calculation of the final relative uncertainty in sigma f there. Okay, so let's put some numbers in now. I'm just following the lab manual here. Suppose that we are going to take the radius to be 0.245 plus or minus 0.002 meters, and take the mass to be 0.95 plus or minus 0.004 kilograms. Okay, so we can just go ahead and put this stuff into our expression right here. And when we do that, and as well as in our original expression for f down here, when we do that, we're going to find that f is equal to 15.4219 kilograms per meter cubed, and sigma f is 0.3832 kilograms per meter cubed. Okay, so how do we quote our final result? Here's the thing that I'd like you to do. What you're going to do is you're going to truncate the uncertainty first to 1 or 2 significant figures. So if the leading number is kind of a small number like 1, 2, or 3, then I might normally truncate it at 2 significant figures like 0.38. If the leading number is a larger number like 5, 6, or 7, then I would probably truncate it right here at 1 sig fig. Okay, so let's suppose that we've decided to truncate at 1 sig fig. That's probably fine. So we're going to take sigma sub f to be 0.4 kilograms per meter cubed. Okay, now the key here is that we're going to truncate f to the same decimal place as we truncated sigma f. Okay, so if we kept 2 sig figs, then we're going to truncate it to here, like 15.42 plus or minus 0.38. But if we did to 1 sig fig, then we're going to go to here, like 15.4 plus or minus 0.4. So since we've decided to go to 1 sig fig on the uncertainty, we'll do the same thing here. And we'll say that our final expression then is 15.4 plus or minus 0.4 kilograms per meter cubed. Okay, so let me give some examples of what would be incorrect, and you can probably see why these are incorrect. We're not going to go 15.4 plus or minus 0.3832, and we're not going to go 15.4219 plus or minus 0.4. The key is that we're going to keep the same number of decimal places here in both of these. We'll let the uncertainty decide how many decimal places we should have in the original quantity. Okay? This kind of supplants the rule you might have learned in a high school course or maybe some other course where you talked about errors or just rounding in general. There's a rule for when you multiply things, there's a rule for when you add things, etc. All those rules go out the window. What we're going to do is when we calculate the quantity itself, f, we're going to keep lots of sig figs. Then we're going to calculate the uncertainty, truncate it to either 1 or 2 decimal places, and then truncate f to the same number of sig figs. Okay? Our lab manual has several expressions that you might find to be useful. let me just give you one example. So suppose that we have a function f equals, say, plus or minus a times u to either the plus or minus b times v to the plus or minus c times w to the plus or minus d. Okay, so it's really a product of things to various powers, and the powers could be positive or negative. You can look in the lab manual, then you could try and derive this on your own, but what you'd find is that the relative uncertainty in f, so f's uncertainty divided by the value of f itself, in this case is going to be the sums, the squares of the powers, so b squared times the relative uncertainty, sigma u over u squared, plus c squared times sigma v over v squared plus d squared times sigma w over w squared. Okay, and there are various other expressions in the lab manual as well, but the thing you can see here is what we talked about earlier, that if you have a power plus or minus b there, it ends up being squared and multiplied by the relative uncertainty squared. Okay, let's move on to weighted averages now. So weighted averages. Okay, you know what a regular average is. If you take a regular average, one person gets one value, the other gets the other value, you add them up, divide by 2, or by however many values you're averaging, and that's a regular average. But suppose that, say, you're measuring the speed of light, and you have several measurements of it. So maybe one group in the class measures one value, and they make an estimate of their uncertainty, and another group in the class measures it, and they estimate their uncertainty. And then suppose you're going to take those two values and you want to average them with someone who measured it somewhere else with a piece of equipment that was much, much, much more precise, and they had an uncertainty that was much, much smaller than the first two. So what would be the right way to average those three things? Would you just add them together and divide by 3? In a way, that wouldn't make very much sense, because the person or the group that measured it with the small uncertainty, they should somehow be given more weight. Their measurement of it should be. So that's what a weighted average is. It takes into account the uncertainties in the things themselves when you're taking the average. We're also going to have an expression for the uncertainty in the weighted average, which is also useful to know. Okay, so here's the expression for the weighted average. It's in the lab manual. The weighted average, call it x bar, if we have n things that we're measuring. So suppose we've got x I plus or minus sigma xi. Okay, so the xi's here are measurements. They're all measurements of the same thing, and I here is going to be 1, 2, up to capital N. Okay, so we're gonna measure this thing n times, and we get these different values. All right, so the uncertainties then are sigma xi. So what we're going to do here is calculate the sum, that's the summation symbol there, of xi over sigma xi, and we're going to square the sigma xi. That whole thing divided by the sum of 1 over the sigma xi squared. Now, there's an order of operations that's important here. I think you probably know what it is, and that's that we're going to do the thing in the numerator, this part here, first, add them up, and then we're going to add this up, and once we have those two numbers, then we're going to divide the two numbers. Okay, we're not going to divide them term by term because that would be a different thing. It's not what we're doing. So this is really x1 over sigma x1 squared plus x2 over sigma x2 squared, etc., over 1 over sigma x1 squared plus 1 over sigma x2 squared plus dot dot dot. Okay, so we'll add up the things in the numerator, the things in the denominator, and then that'll be two numbers, and we'll divide those two numbers. So my claim was that this expression is going to favor the measurement that has a small uncertainty, right? That's what we want to do. So let's take a look at a certain limit here. Let's suppose that x1, this guy here, is the one with a tiny, tiny uncertainty. So sigma x1 is a very small number. And in comparison, sigma x2 is a larger number than sigma x1. And same with sigma x3, it's larger than sigma x1. In the limit that sigma x1 is a really, really small number, you can see what's going to happen here. The x1 and the x2, the x3, we're kind of expecting those numbers to be more or less the same size as each other because they're things that we're averaging, right? These are measurements of the same quantity. So when sigma x1 is really small, what's going to happen? Well, we've got x1 divided by something that's very small squared, and this term is going to be much larger than this term or the other terms down here. And when we're looking in the denominator, this term is going to be much larger than these terms here in the limit that sigma x1 is very small. So what's going to happen? We're mostly going to have this divided by that. And in that limit where sigma x1 gets really, really small, that and that cancel each other out, and we mostly get x1. Okay, so the one with the small sigma x is going to be the one that gets favored. Okay, let's take a look at the uncertainty itself now. So we have an expression for the uncertainty in the average, and that's going to be the square root of 1 over the sum of 1 over sigma xi squared. Okay, again, what that means is we're going to take 1 over sigma x1 squared plus 1 over sigma x2 squared plus dot dot dot. And when we're done, take the square root. It's very easy to forget to take the square root here. Okay, so you got to remember to take the square root. All right, a couple of things here. We can take a look at, okay, let's take a look at one limit here again. Let's look at the limit where sigma x1 is much smaller than the other ones. What are we going to have then? Well, in that limit, this number is going to be 1 over a small number squared, and we can neglect these ones by comparison. It'll be 1 over this number, more or less, which will be sigma x1 squared. And then we take the square root, so we get sigma x1. So if one of these uncertainties is really, really small, then to a good approximation, sigma of the average x bar is more or less the value of the one that's much smaller than all the other ones. Okay, let's take a look at a different limit. We've looked at one limit where one of the uncertainties is much smaller than all the others. So let's take a look at the limit where all the uncertainties are the same as each other, because that's kind of instructive as well. So suppose that that sigma x1 is equal to sigma x2 is equal to, etc. They're all equal to each other. We'll just call it sigma x. Okay, they're all the same value as each other. I should mention, I guess I didn't mention this explicitly here, but the sum always goes from 1 up to n. So when I just put an I under that, what I mean is sigma I equals 1 to n of whatever. Okay, that's what that always means. That's a little bit of a shorthand. Okay, so let's suppose that all the sigmas are the same size as each other. what's going to happen then? So then x bar is going to be, well, if they're all the same size, we got the same thing appearing in each of those, we can actually just factor that out. So get 1 over sigma x1 squared times x1 plus x2 plus dot, 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 dot. And then in the denominator, 1 over sigma x squared times 1 plus 1 plus dot, 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 dot. These guys cancel each other, and we end up with just, how many of these are there? 1 plus 1 plus 1 plus 1. That's just n, right? So it's 1 over n times the sum of all the xi. That's just the usual unweighted average. So in the limit where all the uncertainties are equal to each other, the weighted average is just the regular average. Add up the numbers, divide by the number of things. Okay, how about the uncertainty though? This is kind of interesting. So the uncertainty in the average in this case is going to be square root of 1 over sigma x squared times 1 plus 1 plus dot, 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 dot. And what do we get? Well, 1 over n, 1 plus 1 plus 1, etc. is n, divided by sigma x squared. It's downstairs in the denominator, so we've got to flip it over, take the square root. We get sigma x over root n. Well, that's kind of interesting. It says that if you measure this quantity a whole bunch of times, and each time you measure it, they're statistically distributed. They've got maybe different values, x1 and x2, etc. They're distributed around having different values, but each of them has essentially the same uncertainty as each other. Then when you average those things, you get what maybe you would expect if you think about it a little bit. What you get is that you get the regular average, sure, but your uncertainty in the average actually gets smaller because you're averaging values. You're expecting that when you average them, somehow the uncertainty ought to get a little smaller, and that's what you're seeing is exactly what happens. It falls kind of slowly though. If you do 100 measurements, then your uncertainty in the average falls by a factor of 10. Okay, it only falls like the square root of the number of measurements, so that is kind of a little bit small. In experimental physics, in particular in my field, in particle physics, experimentalists will refer to this as getting more statistics. They'll do an experiment, they'll let it run for a long time, and then they'll go get a grant to get some more money so that they could take much, much more data. And if they get 100 times more data, then they can expect that maybe their uncertainties are going to fall by a factor of 10 so that they can basically make more precise measurements of things. Okay, and that's what we're seeing here. You get a 1 over root n improvement or decrease in the size of the uncertainty.